Well, thank you very much. Thanks, Professor Ponda, for inviting me for this presenting all this stuff, what I know about smart grid. And as my talk will proceed, you will know my knowledge on smart grid is not zero but negative. So what I will do today, we'll have some, you can interrupt me at any time, although Koiballa told that you should not interrupt in the middle. But sometimes you can interrupt me. Can you, all of you can hear me?
Yes, sir. Yes.
All the people, anybody in the audience?
Yeah, participants, can you respond that
Yes.
is it audible?
Yes, sir.
Yes, sir.
Okay. So if you want to show your face also, I'll be happy to see your face so that how you react, I can know. Okay.
Sir. Audible.
No problem. This title of this topic is Smart Grid Control. Why? That means why we should control, what we should control, when we should control, and how we should control. Okay. So we'll talk about those things. What I will not talk, that I'm going to tell. I will never talk about the smart grid because all the presenters who will come after me and who have already come, they have told about smart grid, right? So there is no point in telling what is smart grid, how it works, all these things. I will only focus my talk on these things. Just 1, 2, 3, 4 points. I'll just quickly cover. But I will focus on point 6 and point 7 later on. After half an hour of my talk, then 1 hour we'll spend on these things. Okay. Where we should start? Because the whole problem is I cannot see you, I cannot know your reaction. So that is the problem in this online platform. See, what I understand from my experience, why ATAL we are now talking about renewable energy and the so-called smart grid which is coming. I understand it is because of the global warming, one of the major consequences of the carbon dioxide emission. So people are interested. See here, I'm just going to, these things I will go very quickly. I will emphasize later on. After half an hour, you will know what I want to talk, not now. About 25% of the anthropogenic carbon dioxide equivalent emissions are caused by fossil fuel-based power generation. This is more than from any other economic sector. So therefore, it is the power generation which is creating problem. And we can say it is the power system people who really create problems. Because the generation which is really, because of the fossil fuel-based plants. So there is an urgent need for significant reduction of carbon dioxide emission from power generation. This is the point. Remember, for past half an hour, my talk has not started. My talk will start later on, 1 minute. This will involve many-fold increase in renewable energy generation and integration. I will tell you a little bit of a story here. Nowadays, you are all academics. I understand nowadays, let us talk formally, that is better. Nowadays, a fashionable catchword. What is that? Machine learning and artificial intelligence. Machine learning and AI has become a fashionable catchword in the engineering and scientific community. Any student you ask, they will feel proud that they are working on machine learning. Which area you are working? I am working on bloody machine learning. What the hell you are doing? No, I am working on neural network. And why neural network? You tell neural network. Why you are saying you are talking machine learning? Machine learning, artificial intelligence, deep learning, this has become the fashionable catchword nowadays in the engineering and scientific community. In the energy sector, smart grid, smart grid, smart grid. People are talking about smart grid. Which area you are working? I'm working on smart grid. As my talk will proceed, you will know, actually smart grid has nothing to do with the power system. We'll see. Power system is existing, that's fine. Smart grid has to do with something with smart communication, with sensors, smart actuators, cloud computing. So all these things, integration that gives rise to the smart grid. Okay, so we'll talk on that. That is a fashionable catchword. And as your career will begin, you will know you will come across many fashionable catchwords as time progresses. Now, deep learning, machine intelligence, machine learning, artificial intelligence, oh dear. Anyhow, we have to somehow reduce the global warming. Now, decarbonization is very important part. And the question is, only one point I'm emphasizing here, the red point here. Decarbonization through renewable energy is easier, faster, and cheaper than in other sectors. So that is the easiest way. If you want to reduce the percentage of carbon dioxide emission, it is always better to generate your energy from renewable energy sources rather than from fossil fuel power. Now, the question is, can the traditional power grid meet the requirements of a smart grid? The answer is no. Why? Let us go to the traditional power grid, then we will come to this point later on. In a traditional power grid, you know that the power generation, there's a transmission grid, there's a distribution grid. The power is generated remotely, it gets transmitted, then it gets distributed. But that is not the point. The point is the traditional electric power grid is unidirectional in nature. This is very important. Where the electricity flows from power generation facilities to the end users. That is important. Traditional power grid is unidirectional in nature. And second thing is, there is only consumer. You consume the electricity, you do not send electricity back to the grid. We'll come to that point. Where the electricity flows from power generation to facilities, fundamentally the grid is optimized to move electricity generated at large, primarily fossil fuel-based centralized generating units, through a one-way transmission and distribution system to consuming devices. Unidirectional is the key in the traditional power grid. And we want to do the modernization. What I will do, I will pass on my slides to all of you. I will ask Koivalya to send it to you later on. Don't worry for that. Now let us start. Bit relax now, relax. All this boring stuff gone now. Smart grid, oh dear. Smart grid. Definitions is there in the screen, you can see it. I will tell you a story, not story, the fact. In the early 16th century, 1500 something, 1400, end of the 1400, 1500, 16th century, there was a spiritual master in India. He is essentially from South India, but he was born and brought up in Banaras. Because you are the Indian audience, therefore I'm telling you. His name is Vallabhacharya. You must have heard his name. So what he has done, he has written a poem, I will come to that point, where he has described the glory of Lord Krishna. And while he is describing in that poem, it has got 8 stanzas. That is called Madhurastakam. And that particular poem always tells everything is beautiful. See, everything is beautiful about God. His face is beautiful. His lips is beautiful. His flute is beautiful. His, you see, whatever is do, Adharam, Madhuram, you must have heard these things. Have you heard it? Yes or no?
Yes, sir. Yes, sir.
Yes. Now see that Madhurastakam, where Sri Vallabhacharya has told that everything about God is beautiful. Adharam Madhuram, Vadanam Madhuram, Hasitam Madhuram, Nayanam Madhuram, his eyes are beautiful. Panir Madhuram, his hands are beautiful. Padam Madhuram, his legs are beautiful. Everything, you just name it, everything is beautiful. In smart grid context, I will tell you, everything is smart. Everything is smart. The sensor is smart. The actuator is smart. The computing platform is smart. Everything, whatever you say, everything is smart. So in a smart grid, there is nothing dumb. Everything is smart. The communication technology, the sensors technology, the actuator technology, everything is smart. Okay. So it is smart grid, everything is smart. Now there is a problem. When everything becomes smart, it is very difficult. You see, I will find you are all academics. I will tell you a story here. You must have observed, academics have got strong sense of ego. Strong sense of ego. They don't want to listen. Say, for example, today there are, as Professor Ponda told, that 220 participants have registered and hardly 30, 45, 40 people are there. It is because they are academics. They do not want to listen. They want to only talk. And also another thing is, if someone is working in a power system, he thinks the power system is best. Somebody is working in a control system, he thinks control is best. Somebody is working in power electronics, he thinks power electronics is best. So to coordinate amongst the academics is an extremely difficult job. Because they all are intelligent, the so-called intelligence. Exactly the same thing happens in smart grid. Everything is smart. The sensor is smart, the actuator is smart, the platform, the computing platform is smart. When everybody is smart, then coordination among themselves becomes not a difficult task, it is an extremely difficult task. It's a bloody hell, actually, because everything is smart. Okay. I'm not telling about this, some key features of the benefits of a smart grid. You can read it because I don't want to spend time on this. Okay, because this is all boring stuff. Smart grid, what it will do, because many other people, they will talk about these things. How load handling is done, how the energy management is done, all these things. Just roughly, the conventional power grid and smart power grid. Conventional power grid is dumb, smart power grid is intelligent. From technological point of view, it is electromechanical, it is digital. Power distribution unidirectional, here it is bidirectional. The generation is centralized, here generation is distributed. There are few sensors, now sensors throughout. Here there is a manual monitoring, self-monitoring, distillation manual, self-healing. equipment failure and blackouts, but there's a possibility of islanding here in the smart grid. Limited control, pervasive control. Everywhere control, control, control. Smart grid, because all the elements are intelligent and it becomes very difficult to coordinate. So therefore, control is the key in the smart grid. Not that I am working on control theory, therefore I'm telling. You can ask to Professor Ponda, he has done lots of work in converters. You can find the papers in Google Scholar, you can go and see. And control is the key. So, customer choices, forget about that. Customer doesn't have choice in traditional grid, and now you have got many choices. Typical smart grid diagram is there. I'm not entering into that. Key elements of smart grid is sensors and actuators. As I told you, they're all smart sensors and actuators, and many of which are power electronics components. I will discuss these things after some time. Communication infrastructure, cloud-based computers, computational platform. The real problem is how to take into account the characteristics and requirements of the increasingly uncertain, dynamic, large-scale, closed-loop power system. Each term has got some meaning. Smart grid, it consists of renewable energy sources. Microgrid, which consists of several renewable energy sources, is part of the smart grid. It is not the entire smart grid. Microgrid is a subset of smart grid, but microgrid consists of distributed generators, essentially renewable energy generation. The problem is, in the renewable energy generation, I'm telling these points I will emphasize now. Uncertainty, wind power, photovoltaic, there's all uncertainty. With renewables, the control of generation becomes significantly more challenging because of increased intermittency and uncertainty. That has to be taken into consideration. But to maintain the frequency, we have to make the balance here. So how to do these things? Prevalence of power electronics devices. I will come to this point later on, just a minute. And the emergence of the microgrid. Now I will tell you, I'm just writing here, then it will be clear. So far what I talked, I will summarize one point before I proceed. The traditional power grid is unidirectional. Traditional power grid is unidirectional. The smart grid is bidirectional. This is the point. First point. Second point is here we have got fossil fuel generation. Here we have got renewable generation, renewable sources. Now the real problem comes. What is the problem? This point I will see from now onwards, I will tell you many analogy, and through analogy I will explain many things. You say, because all of you are academics, and normally the undergraduate students are asked to perform an experiment, if electrical students, synchronization of alternators. Synchronization of alternators in the laboratory. You see, the synchronous machines has got lots of inertia. The traditional power grid has got lots of inertia. If something happens in the grid, then the machine can take care of that because it has its own inertia. I will give an analogy just a minute. But the problem with the renewable energy sources is the problem with the inertia. Absent, almost absent. Why? This point is critical point. I'm explaining these things, I'll emphasize. Renewable energy sources cannot be directly connected to the grid. It has to be connected through power electronics devices. Okay. Now, whenever you are connecting the renewable energy sources through power electronics devices, then the inertia is no longer present. This is just like here. I'll tell you, these renewable energy sources are just like the guests in your house. They are the guests in your house. They are not members of your household. See, understand this point very carefully. Not the members of house. So what this renewable energy sources will do, what the guest will do, suppose a guest is coming to your house, what he will do? He will be in your house. He will be enjoying everything in your house. But if there is a problem in your house, he will say, that is your bloody problem. I am not bothered. I am going away. You go. You solve your problem. That is your problem. Because I am not a part of your family. See the point. They are the guests. So, if everything is going okay, they are fine. The moment there is some problem, they will say, that is your problem. It is your house. I have just a guest. So better you take care of her. I'm not bothered. Now the problem is how to tackle this particular inertia support, how to give it. So they are the guests in the house. They are not the members of the house. So if some problem occurs in the present grid, and there are lots of renewable energy sources, very difficult to manage. Whereas in the traditional power grid, there are synchronous machines. They have the inertia, so they will manage. That's the point. It's because the traditional in the renewable energy sources, there is a power electronics converters, inverters, they are present. And they actually decouple the system. They don't provide any inertia. Okay. So inertia is the important point. And uncertainty is no doubt is there. So another thing, the power electronic systems that interface distributed generators with the grid must operate under feedback control at multiple time scales. If distribution grid voltages are to be kept with the required tight constants. Certain tricks, things I am going to tell you now, multiple time scales. Very typical thing in control theory. Multiple time scales. What is multiple time scales? Let us see the analogy I will give you the multiple time scales. Some of you who are working in drives, electrical engineers, you must be working with electric drives. I'm just writing here. Electric drives. Multiple time scales. You see, many things I will give you the concept only. Electric drives. It has got a speed loop. Then I will give an analogy later on. That it has got a speed control loop and there is a current loop. the two loops. For a particular speed, you require a particular current, and the current will be provided by the current loop. And this one is much faster, and the speed loop is slower. Have any of you done such type of things? Electric drives? Any answers? Yes or no? Electric drives, if you have worked while you are controlling the speed of a machine by using a current signal, there is a current controller and there is a speed controller. Current controller, current loop controller, and here the speed controller, speed loop controller. This one is slower and this one is faster. Have anybody have done it? If not, just tell me.
No, sir.
Okay. So you will find that the two loops are, one is very fast, multiple times, 2 time scales. Okay. Say for example, if this one is working at 10 millisecond current loop, this one will be say 330 times, 300 milliseconds. Yes, slower. Because the machine speed has to be controlled. The speed machine has got the inertia, and current loop is controlled by power electronics devices, so it is faster. Multiple times. It's a 2 time scale, but there are multiple time scales. I will give an analogy to understand the multiple time scales, and it's very important in a smart grid context. I will tell you why. I have got a friend. He is now currently working in Bombay. I'll tell you a story. I'm not taking his name. So he was telling, whenever he comes from Bombay to Bhubaneswar, you know Bhubaneswar, yes or no? Many of these staffs who are not from Odisha, they should know that Bhubaneswar is the state capital of Odisha. So whenever he comes to on a holiday to his house, see the multiple time scale. His mom, from the very beginning, from the early morning, will tell, okay, we will go and buy these things. Then after 5 minutes, he will say, oh, okay, we will go and please buy these things. Again, after half an hour, he will say, okay, let us buy these things. Because the son has come from Bombay, so he will go on telling. Then the son will tell, okay, you just go on telling. I'm not listening. I will go only at evening time to the market. I will go on the shopping complex at the evening. You go on telling. You see the multiple time scale. You see the mother, what the mother is telling. See the point. Mother is telling, say, half an hour interval or 30 minutes interval. He's working. Mother is telling now, 5 o'clock he told, bring these things. Next 5:30, bring these things. 6 o'clock, 6:30, he will go on talking throughout the day. The son, he said, no, I'm not working. You go on talking. Whatever you have told me in the entire day, I will go on evening 6 p.m. to the shopping complex. So you operate your time sampling interval TS is 30 minutes. My sampling is TS1. My operation is 12 hours. I will go in the evening. You start talking from 6 o'clock. So you see 6 o'clock, 6 a.m. to 6 p.m. operating a 30 minutes interval, talking this, bring this, bring this, bring this, bring this, bring this, bring this. But the actuator is operating at a different time scale. It is not, it is just collecting all this information, but it will operate, it will go to the shopping complex at 6 p.m. It is not working at 30 minutes interval. You bring these things, it doesn't mean that he will go and go to the shopping complex and bring it. Because by the time he brings, then again he will say, you bring another one. See the multiple time scales. In the smart grid context, why it is important, I'll tell you. Important in the sense, in the smart grid, remember one point again I'm emphasizing, the renewable energy sources, the power electronics devices has to be integrated with the renewable energy sources. Otherwise, these sources cannot be connected, cannot inject power. And these power electronics devices operates in the millisecond interval. Whereas in the smart grid, many decisions related to market, economy, it has to be taken by the human beings. And that scale is different, maybe days, maybe weeks. So multiple time scale operations. In the smart grid entity, there are so many elements and each has its own time scale. Power electronics devices operate at a different time scale. The human beings operate at different time scales. And the other devices, they operate at different time scales. So that point you have to understand, multiple time scale. Okay. Any doubt here? Any doubt about the multiple time scale? No answer. That means you have not listening or you have understood it.
No, sir, no doubts.
Okay. Thank you. Thank you. So multiple time scales. This is a very crucial point. Inertia is not there and multiple time scales. So therefore, we want different types of control. And another control term you might have come across, transactive control. Transactive control, that is essentially a market-centric control. Because now, you see, I will tell you here, in the smart grid, another important point which I will emphasize here, the consumers becomes prosumers. What is prosumer? That means the person, you are the consumer, you are consuming the electricity before. Now, you can consume electricity at some time. At some other time, when you are generating more electricity, you can inject that electricity to the supply system. So you are a producer as well as the consumer. Prosumer means you are a producer of electricity plus consumer, depending on the timing. So the consumer becomes a prosumer. The power flow becomes bidirectional. Okay. The system has to operate in multiple time scales and everything is smart. And most of the computation has to be done in the cloud-based platform. Now everything is on the cloud. Okay. See here, smart grids are in fact a complex, multifaceted cyber physical systems. Again, catchword, cyber physical systems. Oh dear. I have got a student working on security of cyber physical systems. Oh dear. So many terms nowadays, you cannot imagine. The linear flow of electricity from generation to transmission to distribution, culminating at the customer connection, is giving way to a much richer ecosystem, more distributed energy assets, two-way electricity flow, see here, extensive cyber elements, multiple layers of decision. Earlier, there was only one layer. The chief engineer was taking decision. Now, many people are taking decisions. Additional active stakeholders. Consumers becomes prosumers. So the things becomes very complex. And also, the notion of a smart grid is not static, it is dynamic. Every day, everything is changing. Every time, things are changing. At what time the consumer becomes prosumer, you never know. You are generating power now, you will inject it. So it is no longer static. Okay. Now, from the increasing penetration of intermittent wind and solar generation, multiple insertion and control points of renewable sources, engagement of customers as active participants, that is the expansion of the role of customers from consumers to prosumers, from power electronics that operates in milliseconds or less to market mechanisms that unfold over weeks or longer. See the multiple time scale. The phenomena and the challenges span a wide temporal spectrum. Now, given the complexity, uncertainty, and dynamics, control is a key discipline for addressing these challenges. See, this is the summary. Don't worry for that. I will ask Professor Ponda to organize to give this handout to you. In this talk, we will focus on the microgrid side. Microgrid, remember, microgrid is a subset of smart grid. It is not a smart grid. Okay? It consists of several renewable energy sources, say wind, solar. I'm not talking, many other people will talk, energy, biomass. This is just for the sake of completeness. What is a microgrid? You know it. It is a microgrid is a group of interconnected loads and distributed energy sources within clearly defined electrical boundaries that acts as a single controllable entity. That is important with respect to the grid. This is the microgrid architecture. I'm not talking, I'll talk about the control aspect just now. This is the microgrid architecture. I'm not, this is for the sake of completeness. After half an hour, I'm just going to the original subject. Why to control distribution grids? Distributed generation from renewable sources such as sunlight and wind represents a key driver for smart grids. These sources are leading the transformation of power grids from a centralized, static, and rigid system. Each term has got a meaning. Centralized, static, rigid system towards a distributed, dynamic, and flexible system. The traditional power grid is a centralized, it is static, it is rigid. But it is now changing to different. It is going to distributed, dynamic, and flexible. And that creates problem. There is voltage fluctuation, there is frequency fluctuation, there is active power flow fluctuation, there is reactive power flow fluctuations. All these things comes into picture. The important point is to coordinate these increasingly large-scale spatio-temporal injections. Spatio-temporal injections, both different as well as time. Spatio-temporal injections. Now let us come. Yes, the subject start. Okay. You are all academics. Is there anybody from industry here? Hello? Anybody from industry? That means
no, sir, there is no one from the industry, sir. Yes, sir. All are from academics.
All are from academics, right?
Yes, sir.
Now let us see control. Smart grid control. Forget about smart grid control. Is it necessary? First question is, I will tell you this particular thing. You are all academics. If you understand what I am going to talk within coming 5-10 minutes, your understanding of control theory will be clear by 70%. Only one analogy. What is the question? Question is it necessary to use a controller? Let us understand this point clearly, then we'll see. You will be surprised. 3 years back, 2 years back, there was a group of students, undergraduate students, that are doing project with me. I asked them to do something on power quality. They did a good job. They also published a paper in IET. The paper has been cited by 14 times now. And we are talking about wavelet, S transform and generalized Fourier transform. Recently, I'm not naming these things. You can go to Google Scholar, you can find out. Someone from India is working deep learning technique in power quality estimation. Deep learning. Many of you must have heard the term deep learning, a convolutional neural network, deep learning. My question is, earlier simple Fourier transform could classify the power quality. Short time Fourier transform can do the job also. Wavelet transform can do it. S transform, Stockel transform can do it. That is more than enough. Is it necessary that deep learning is there, therefore you will use it? You are the academics. You try to understand these things. I'm just trying to share my experience. Why the hell I should use a deep learning algorithm? Deep learning has been devised to do something else, not to classify your power quality. Right? But they did it and they got it published in some international journals. People read it and many people will cite. Does it have any meaning? Research contribution there, nothing, because this guy did not do anything. Deep learning, the program is available, software is available, just plug in. And this is deep learning, which I will never encourage to all of you academics here, sitting here, because I am in this profession for last 34 years and this university for last 18 years, now 19 years. Do not do certain things which is not necessary. Deep learning is it necessary to use for power quality classification? And how much accuracy they get? Wavelet will give the accuracy of 97%, and the deep learning is giving the accuracy of 97.2%. Is it necessary? It is absolutely ridiculous. So similarly, let us see, is it necessary to use a controller? Please concentrate here, because this is a very important point I want to say. I'm giving the analogy here. Suppose you have got a child, he goes to school today. He goes to school today. Secondary school, let's say high school. Higher secondary, go to school today. The question is, if he goes to school today, will you employ a private tutor to teach him? Because the time is short, I'm just giving the answer. Certainly we will not do that. So what we will do? If the student is, your child is going to school today, so what you will do? You will wait till the first test is done, is taken by the school, by the teacher. First test, open loop, no tutor. Suppose your child, see here, I'm just giving the analogy here. Suppose your child has taken these subjects: physics, chemistry, mathematics, and English. He has taken these subjects. So he has gone to school today. My question is, are you going to employ a private tutor? The answer is no. not at least. You wait. First you wait and check his performance in the open loop. That means his performance without a tutor, additional tutor. Now see, after test 1, class test, suppose this is the mark. The mark is, suppose in physics, he has scored 90. In chemistry, he has scored 85. In mathematics, he has scored 20. And English, he has scored 70. This is the mark after first test. Open loop performance of the child, open loop performance of the system. First you study. That means the performance of the system without the controller, without the tutor. Tutor is the controller. I need an answer from all of you. After the first test, if this is the mark, do you need a tutor or you don't need a tutor? Anybody can tell? Your child has scored in physics 90 marks, chemistry 85 marks, mathematics 20 out of 100, and English 70. Do we need a tutor now? Please answer. Your academics, you can answer. Yes, it is required. No, you can talk instead of writing. Yes.
It will be required for the mathematics subject,
Yes.
sir.
So you require a tutor. Work quick. Now I'm coming to this point. That's good. Thank you very much. You can talk, no problem. You require a tutor. Now you require a tutor, that's fine. A controller is necessary. Who is tutor? That is what we will discuss in the coming half an hour, 45 minutes. In this case, you require an appropriate tutor. Tutor is a controller. Now, in this case, if your child mark is less in mathematics, you cannot go to the Bombay local station and tell that my son's performance is bad. I want someone to come to my house to teach. Will you do that? Then anybody can come. Okay? So in this case, you require a person with mathematics qualification. Yes or no? If
Yes,
you
sir.
employ a person of economics background or a person with literature who doesn't know mathematics, if he comes there into your house, can he improve the performance of your child? Yes or no? No.
Sir.
Right? Hello? Hello? You please answer, otherwise the dynamics is lost. Appropriate tutor. Yes, please.
Yes,
Sir, can I interrupt for 1 second? Sir,
Yes.
actually we have asked the participants to mute their audio.
Okay.
Because-
Now, I think
because-
let them talk a little bit. Let them talk.
No, otherwise it will create a disturbance, sir.
Okay.
Because many participants are there.
Okay,
That is the main reason.
Okay. So now
Yeah,
see, the
yeah.
appropriate tutor here is a mathematics graduate. Because your child has got mark less. I'm not entering further detail into that. Now, suppose in this case, let us say you say that the open loop performance is bad. I'm using interchangeable the control terms here. The performance of the open loop says the number in the mathematics is poor. So you require a mathematics tutor, and suppose you employ. Yes. So now suppose you are taking decision. Suppose a tutor, appropriate tutor came. You employ a controller. The question is, can you guarantee that with this tutor, the performance of your child will improve. This is the key point. The performance of a child in mathematics is bad. You employ a mathematics graduate to teach him extra. Can you guarantee that in test 2, the performance will improve? Can you guarantee? See, I'm writing here. Can you ensure test 2 performance will be better? This is the key point. See here, your child, you are an engineer. You also know mathematics. You can also teach your child at home. But your child is not listening to you. He or she is not listening either to you or to your husband or wife, whatever it may be. How do you say that your child will listen to that mathematics tutor who is coming from outside? So the possibility is, if your child is the system, is uncontrollable, then it is a futile exercise. If the system is uncontrollable, then there is no point. So before you employ a controller, first you would study the open loop performance. Second, you study the controllability of the system. If the system is controllable, then you design an appropriate controller. If the system is not controllable, there is no point that you should employ any controller. That is the crucial point. And we'll proceed now further. These are the different types of control things: voltage, frequency regulation, smart grid. And the slides are there. You see so many types of controllers people are using. I will talk about some features of some key features of some of the controllers. One of the controller, no matter what sort of controller you develop, what sort of controller is being developed, the industry people will never go away from the PID controller. PID controller has been very popular in industry, and it will continue to become popular, no matter what sort of development occurs in control theory. What the PID controller does, for the academics who are not in the control field, I am just telling you the philosophy of different controllers. Then you decide which one you will use. First one is PID controller. Its equation is given like this: the output of the controller, Kp into error, integration of the error, derivative of the error. I will give an analogy shortly, just a minute. The proportional, this PID controller has got 3 components. One is the proportional component, another is the integral component, another is derivative component. The proportional controller will work. How much is the error? How much is the error? The proportional action. I will give the analogy shortly, 1 minute. The integral controller that acts based on how long the error has persisted. And the derivative action will tell you how the error is changing over time. So the analogy I'm giving you here, suppose a student is there in your class and you see that from in mathematics, suppose in electrical circuits, suppose in electrical circuits, his mark, he scored out of 100, 35. Instead of say around 90, 95, say ideally 100, he has scored 35. So now you know that the mark scored by the student is very low from the desired value. So the proportional action will be more here because the error is too high. How much is the error? The second point is interesting. How long the error has persisted? The integral action will decide whether this particular student has scored this low mark in this particular semester or his performance is bad in the last semesters, even in the school, even from the childhood. How long the error has persisted. That means this lower mark he is getting, how long it is persisted. Is it the only one? Suppose it might be outlier. That means in this particular semester, he has done bad. But in the other semesters, he has done good. Then the integral controller will not very active. But if the performance of the student is very bad from the very beginning, that means from the childhood, he is a bloody idiot. He is not the idiot now. Okay, then the integral controller will take. How long the error has been persisted. The derivative controller is another point. He is not bothered how much is the error. He is not bothered how long the error has persisted. He will take how the error is changing. He will see, okay, this semester, he has scored from circuit theory 35. In a previous semester, whether he has scored 65, previous semester, whether he has scored 85, see the error is changing. If error is changing, that means the performance is not consistent, then this derivative action will take into account. So remember here, I'll tell you what happens for the students who work in control theory. I'll tell you. In the transient phase, this is the transient phase. When error is changing, so dET over dt will be some value in the transient phase. The change of error. In the steady state, when the error is constant, this particular term will be 0. So therefore, no matter what you do, derivative controller will not improve the steady state performance. No matter what you do. Because in the steady state, the error is constant. So this dET over dt will be 0. The action because of KD derivative controller will be 0. So what the students normally do, even the PhD students, they will try to eliminate the steady state error and they go on varying the derivative again. That's completely useless. But steady state error cannot be changed by derivative again because the steady state the error is constant. So dET over dt is 0. The steady state error will only go because of the integral controller. Integral controller is a very important controller in any engineering application because that will reduce the steady state error to 0. No other controller has got the capability to reduce the steady state error to 0. So remember, this is extremely important. Integral controller has to be used in most of the applications because steady state error has to be 0. Okay. Now this is a PID controller. In microgrid control, some of the presenter will talk about a droop control. It's very extensively being used. In a conventional power grid, we use the droop control techniques. So many times the droop control method is being used. Okay, but I will not talk on that. I will talk about another very extremely powerful controller that is called the feedback linearizing controller. Let us discuss about these things a little bit. Extremely powerful controller, and many I have seen in power system applications, many people have used it, but you must understand the concept behind the feedback linearizing controller. Now, most of the systems are nonlinear in nature. Now, when most of the systems are nonlinear in nature, it is assumed, if you don't know, that is a different thing. It is assumed that you are an expert in linear control systems. You are an expert in designing linear controllers. This is assumption. You know about linear systems. You know how to design controller for linear systems. But suppose the system is nonlinear. So what the feedback linearizing controller will do, it will cancel the nonlinear term first and make the system linear. Then the equivalent linear system, you design any linear control theory. So you cancel the controller has got two parts. One part, it will cancel the nonlinear element. And the second component, it will control the plant. And the second component will be designed using the linear theory, because by the time the system is linear. Now see here, example here I'm giving, x1 dot is equal to x2, x2 dot is equal to minus ax1 minus bx2 minus cx1q plus u. See here. So there is a nonlinear element x1q, cx1q here. And that creates the problem. So what I will do, I will design a controller. I will design a controller here. This one. U is equal to plus cx1q. So this particular part will cancel this nonlinear element. And the other part, V, the system becomes linear and you design depending on what you want to achieve. See, V you can design by using any standard linear technique. Okay. It is, I'm just giving an analogy like this. So for example, you are in academics and you are entering into the classroom to teach the students. And someone told you in the classroom, there are some students, not all the students are there. There are some outside elements who wants to create disturbance. They are also present. Suppose someone tells you that you are going to the class. In the classroom, not only students are there are some outside unsocial elements, people, they are entering into the class. So what you will do, you will not go to the class alone. You take with you a security personnel from the university. Then you tell the security personnel, you do one thing, you find those idiots who are sitting in the class who are not students and you remove them. So the security personnel will remove the students, then you teach. Sorry, remove the unsocial people, then you teach. So now in the classroom, not the lecturer alone is going. Lecturer is going plus a security person is going. The objective of the security person is to cancel the nonlinearity and then you teach. So this is exactly the feedback linearizing controller. Okay. Very powerful controller, being extensively used in many engineering applications. Okay. And remember here, it requires lots of mathematics. I'm not telling those mathematics because we don't have time here. So, there are lots of mathematics. But if you want to know about this mathematics, you have to study the Lie algebra. It is simple, and it requires the knowledge of Lie algebra to design a feedback linearizing controller. I'm just showing it here. And see here, this is a DC microgrid. It has got fuel cell, PV cell, battery energy storage systems. Now, each of the systems are nonlinear in nature. Now, see here, feedback linearization technique decouples an interconnected system into several subsystems based on the number of control inputs, and the controller can be designed for each subsystem in a decentralized way. So people have done some work on the DC microgrid control, but remember the concept of the feedback linearizing controller is cancel the nonlinearity. Cancel that bloody idiot who is there, who is creating problem. You see, when we teach to the students, we tell them, just cancel them. If there is a nonlinearity who is creating problem, why to keep it? Leave it. Let it go to Pacific Ocean. Okay. Because our university's Pacific is hardly 1 kilometer. So I always say, let that nonlinearity go into the Pacific, dump it, then design your controller. Feedback linearizing controller, PID controller. Next is layout based controller design. Layout based controller design, see, I'll tell you, this is an extremely powerful method, and until now, no other methods have been devised to analyze the stability any control theory, any system you are designing. Stability is the most important point. I will explain you what is the meaning of the stability. This is the extremely important point. What is stability? The system performance may be bad, little bit. We can tolerate. But no matter what happens, you may design a fuzzy controller. You may design a robust controller. You may design a H-infinite controller. You may design a sliding mode controller. You may design a neural network controller. You may design a linear quadratic regulator, linear quadratic Gaussian controller. You may design an optimal controller. You may design any controller, doesn't matter. At the end of the day, the system must be stable. If the system is not stable, you have to prove it mathematically. You have to prove it mathematically that the system is stable. What is the meaning of stable? I always give this analogy and it will be clear to you. Remember the performance of a student. Suppose a student is there in your class. Suppose you have got a student in the class and he gets, say, C grade. C, B, A, let us say 3 grades for the C grade. He's not a very good student. Still, university will keep him. Okay, he has got C grade, doesn't matter. But if a student is mad, he has got some psychological aberration, he is a mental patient and completely mad, then the university will say, you are not allowed to sit in the class, you have got some psychological aberration, you should be put in the mental hospital. Because the society will not admit those people. They will say your place is a different place. Similarly, suppose a particular student is doing very good or bad, but is a criminal. If he's a criminal, his performance is good, but he's a criminal. He's creating crime. He is not allowed in the class. He should be put inside the jail. Similarly, the stability. No matter what you do, the system must be stable. Okay, that is extremely important point. And then how to study the stability of the system? How to study? Now, for linear systems, we have got the theory developed already. For linear systems, we know if the eigenvalues or the poles are in the left half of the S-plane, it is stable. For nonlinear systems, it is difficult. In nonlinear system, stability is studied. Until now, we are doing the same thing. No other methods have been found out. Lyapunov stability. Lyapunov is a person, Alexander Mikhail Lyapunov, a Russian mathematician who has given the concept of stability for nonlinear systems. So what it does, Lyapunov stability, the concept I'm telling you, and you will use it even if you are using designing control of a smart grid. What you have to do, like this. You describe the energy of the system. The concept is like this. Describe the energy of the system by a function, say Vx. And we say the Lyapunov function to respect Lyapunov. First, you find the energy of the system and describe it by a Vx. Then you differentiate this function. Differentiate this function. That means you get V dot x. If V dot x is negative, the system is stable. Okay. This is true with all of us, because suppose you have taken food in the morning, as time progresses, your energy will come down. So in the morning, you speak at a higher voice, high tone, high pitch. So as the time progresses, your energy goes down. Then you become dormant because you are stable. As time progresses, when your food becomes less and less, that means it's negative. V dot x is negative, system is stable, right? Now, if this is the case, then nonlinear system stability studies, we are using the Lyapunov. Remember, I'm again telling you, no matter which type of controller you are designing, you have to prove the stability. That's a must. In power system, fortunately, in power system, the system has got enough damping and the system is inherently stable no matter which type of controllers you are using, most of the cases. But it's not the case in other type of systems. So power system people are very lucky. Okay, that system has got enough damping and the stability is not a major issue. But however, if you are designing controllers for other systems, then stability is a must. Otherwise, the reviewer will take your paper, he will just throw your paper into the dustbin and tell the stability is not proved, go. Because the paper has no value. Now, if the concept is very simple, you take a function and differentiate it. And if it's negative, system is stable, right? Remember, until now, I'm giving the concept, until now, you in the school, in colleges, in most of our applications, we solve a set of equations. We solve, what we do? We solve a set of equations. But, so this equality, that is from the mathematical point of view, we solve equality. Ax is equal to b. This is the equations we solve. You all know how to solve it. This is easy. Ax is equal to b. What is x? X is equal to a inverse b. X is equal to a inverse b, and it will give you an unique solution if the equations are well conditioned. Okay. The problem is, suppose you have been asked find x such that, see the problem. Understand the problem first. X is less than b. This is the crucial point. This is the crucial point. X, this is an inequality. This is not an equality. And the solution of x is not unique. A into x is less than b. So many values of x can satisfy that particular condition. So solving a solution of an inequality is not an easy task. Okay. So therefore, although the concept looks very simple, that you describe the energy of the system by a function, differentiate that particular function, b if it's negative, v dot x should be, the stability condition says, v dot x should be less than 0. Inequality. Remember, this is inequality. Because you are academics, I'm telling you, to solve these things, we have to go to many sophisticated mathematics, semi-definite programming, and the standard software is available. One of these software is YALMIP software. You have to use the theory of linear matrix inequality, bilinear matrix inequality, Schur complement. So these are the things where you should use to solve this inequality. And remember, if you are doing some higher level research in control theory, also in smart grid control, using some methods to control it, and the reviewer asks to prove the stability, you have to formulate the problem as an inequality problem and solve it using the semi-definite programming, either using the linear matrix inequality, bilinear matrix inequality. I'm just telling the names. Sum of squares approach. So different approaches, very sophisticated mathematics. And then if you don't do it, nobody will accept it. Another point in the Lyapunov-based controller design is, it is a sufficient condition. That's the problem. That is another problem. Lyapunov stability, which is being used until now, and we are using it, it is a sufficient condition. You find the function Vx, you differentiate it. If it is negative, system is stable. Remember, if v dot x is negative, system is stable. But if v dot x is not negative, you cannot say that system is unstable. This is the beauty. You understand it clearly. You get the function Vx, get v dot x. If it is negative, system is stable. If it is negative, if it is positive, you cannot say it is unstable. So therefore, we say the Lyapunov stability is a sufficient condition for stability. It is not a necessary condition. And this is being extensively used in designing of the controllers. Only 5 minutes is there. Then there is another approach based on this Lyapunov function. Designing of the controllers, you will use it later on. If you, I'm just giving the hints here. Control Lyapunov function. The concept I'm telling you, I'm just here. Concept is like this. In feedback linearizing controller, we cancel the nonlinearity, completely cancel. In feedback linearizing controller, we cancel the nonlinearity and make the system linear, then design the controller, right? But sometimes what happens, there are some useful nonlinearities, which often we do not want to cancel. I have seen in many cases, there are some students who are not very good students, but they are very good to organize functions. Well, suppose you want to get certain things done, you can ask those people. They are not academically good, but they are not useful to solve the linear matrix inequality, but they are very good if you want to arrange a function, you want to get certain things done from outside, so don't cancel them, don't disregard them. And this control Lyapunov function, what it will do, it will retain the useful nonlinearity. This approach, it will retain the useful nonlinearities. It will not completely cancel. You see, such a powerful controller. It will retain the useful nonlinearities and cancel other. And cancel the other. Okay, control Lyapunov function. Professor Ponda, how much time is there?
Sir, only 2-3 minutes left, sir, because 11:30 is the.
11:30. Okay.
Sir.
Then how much time you do for question answer? 5 minutes.
Sir, we'll take
5 minutes.
questions, sir, from now, sir. Otherwise.
Only 1 or 2 questions we will take, sir.
Okay. So I think I cannot consider about the. This is another control. I just tell you a little bit here because we don't have time. One of the controller which is very powerful and is going to be a substitute and more popular in industry is the model predictive controller, MPC. It is nowadays has become a fashionable catchword. Every time power electronics people, MPC, we will design MPC, model predictive controller. Now see, I'm just giving the only concept within 1 minute. This model predictive controller, the whole idea came from the minimum variance controller, but developed in 1973. See, the idea is like this. When the system is acted upon by disturbance, when the system is affected by disturbance, how to manage the soul, how to control it, how to reduce the value, because disturbance will create variations in the output from its mean value, and I want to minimize it. Minimum variance controller. So what it will do, the controller will do, it will predict the disturbance. It will predict the disturbance. And then cancel whatever it predicts, cancel the disturbance. First it will predict. The problem is it cannot predict the full disturbance. The total complete disturbance cannot be predicted by theory. Complete prediction is not possible by mathematics. So therefore, when the system is acted upon by disturbance, you cannot make the variations to zero. So it is not a zero variance controller. It is not a zero variance controller, no. This is a minimum variance controller because you cannot predict this particular thing. And most of the predictive controllers, generalized predictive controller, model algorithm controller, dynamic matrix controller, quadratic dynamic matrix controller, extensively used nowadays in the power system community, power electronics. They are coming from this minimum variance controller. And to finish it, I will tell you, this prediction is done by using a particular identity. That identity has been found in 450 BC by an Indian mathematician. That is called the Aryabhata identity. Other people also in Diophantine identity, Bejout identity, the same thing. Aryabhata found in 450 BC, and in recent years, these people found independently, and this identity is being used to predict the disturbance and cancel it out, and the extremely powerful controller. And present there, the predictive controllers which are being used are based on this particular principle. It will take a hell of a time for me to explain these things, how this is being done. So what I discussed today is like this. Just to summarize within 1 minute, smart grid is a fashionable catchword nowadays. Everything is smart in the smart grid. And I gave you the analogy of a Madhura Ashtakam because you are our Indian audience. Okay? Everything is good. Everything is good of Lord Krishna. Similarly, here everything is smart. The sensor is smart. The actuator is smart. The communication infrastructure is smart. The controller is smart. Everything is smart. When everything is smart, the real problem is how to control it, how to coordinate it. One of the important controller which is extensively being used is the PID controller. It has got three components. One is how much is the error, how long is the error, and how the error is changing. So one will remove the steady state error to zero. Another will improve the transient performance. Next, I told, no matter what you do, now or in future, the stability is a must. You must prove the stability of the system, otherwise it is completely useless. So therefore, the Lyapunov method is to be used. It is based on the concept of energy, but the trouble is mathematical problem is there. Because there you have to solve an inequality. It is not an equality. And the solution of an inequality is not an easy task. You have to go and take the help of sophisticated mathematics like semi-definite programming, linear matrix inequality, bilinear matrix inequality, sum of squares, and all these things. Thank you very much. Then I will take some questions now.
Yes, participants are requested. Or Kavila, any question is there from the participants?
Yeah, I'll just read out one of the question from the participant, sir.
Okay.
She's asked, PI controller is more preferable over PID in industry because D is very sensitive. Can you please elaborate more on this?
No. Who said that PI controller is most preferable in PID? No. It all depends on that. If you want to improve the transient performance, then the derivative controller, you must use it. PI controller, it has got a problem. It will remove the steady state error, but it will make the system response slow. You say, what is the meaning of PI? We have to understand very clearly, because you are all academics, and therefore I'm telling you. See, when you are solving the differential equations, we have to understand the transient and steady state. While solving these equations, differential equation, there are three things. Where you are is the initial condition. First, where you will be, I'll tell you the meaning of this thing, will be is the steady state, the final condition, the particular integral in differential equation, steady state. How you will go from initial to final is the transient. Say, for example, I'll tell you, suppose you see, I'm just 1 minute, suppose all the students are staying in the hostel, then the initial condition is same. They are coming to the classroom. This is the classroom. Now this is the time axis. Now I'm telling the three students. One particular student, all are staying in this hostel. One student he comes from the hostel, then he crosses the college, he moved here and there, and finally come to the classroom. See, this is the student number 1. Student number 2, he came from the hostel, and straight away come to the classroom. This is student number 2. Student number 3, he started from the hostel and he did not go anywhere, but by the time class finishes, you see, he has not reached the steady state. See, student number 3. Suppose he reaches the classroom after much time. Now see, from these 3 students, all of them have same initial condition. All of them has got the same steady state condition. But I will say the student S1, the first student, is a bloody idiot. You see, he started from his house, from the hostel. Instead of directly coming to the lecture, he is moving here and there, you see, oscillating. So it is the transient behavior of the system which will decide whether the system is better or not. Not the steady state, not the initial conditions. And transient behavior can only be improved by derivative controller, not integral controller. So industry people use PID. Without derivative, how can you improve the transient? Many times oscillations occurs. So derivative controller has to be used. And derivative controller increases the stability margin. It will make the system response fast. Integral controller will reduce the stability margin. It will make the system response slow. Although it will reduce the steady state error, it has its own disadvantage. So we take the 3 controllers. Anything?
Yes, sir has explained very nicely, concept-wise. Participant, you have any other doubt? Directly you can ask.
Sir, in line with that question, the same kind of question.
Who is the participant? Let the participant to ask.
Shankar Rao. Can you please unmute and ask the question?
Yes, sir. Thank you, sir. Hello.
Yes,
Hello?
yes. Please go ahead.
Yes, sir. Like actually, I am working controlling of the price. In that, most of the papers I have observed in mostly they prefer PI controller rather than PID. I want to know the reason.
No. You see, I'm not telling about the specific controller. You see, if the system which they have used, the transient performance is satisfactory, then there is no need of using a derivative controller.
Yes, yes.
So that particular, because derivative controller will not work, will aggravate the noise performance. So it is all system dependent. The type of systems you are working, people are using PI controller. That means the system has that's the system concept. That system may not require a derivative controller.
Sir.
But I am telling the derivative controller in most of the cases we use it. Because that is the only controller which can improve the transient response. If your transient response is satisfactory, there is no point in using derivative controller.
Sir. Thank you, sir. He has understood the
Thank you,
system
sir.
based. It should be the system based approach.
Yes.
Sir. Okay, thank you, sir. You have started with the smart grid technology concept, and you have already given the complete idea about the different control techniques with the different analogy also. I was completely attending the class, and I am very. It is really a privilege for us to get the complete lecture from you, and kindly